works. Okay. So if I remind to end the previous session, I ask you to do this one by yourself. Okay? I hope that you have tried. So I have a uniform on the interval 0, 1. And I want you to find the density of exponential of u. Okay? So the density is something that we have already done several times now. Okay? The idea is to use this well, it doesn't work. So the idea is to use this kind of result here that allow me to deduce the density function from the distribution function. Okay? So the idea is to try to find the distribution function of z in order to recover its density computing the derivative. Okay? So if I am interested in the distribution function of z, by definition, the distribution function is the probability that z is less than small x, okay, that I have to find for any x. And here, my z is just the exponential of u, where u follows the uniform on the interval 0, 1. Okay? I have this one. Okay? This won't work, it will be better. So, an idea to do, I said that there is one case that is obvious. Which one? One case where it is very simple to compute this probability.
Where s is smaller than 0
Yeah.
or equal to 0.
What happened in this situation here? An exponential is strictly positive. So what is the probability to be less or equal to 0? 0. So in this situation, okay, I know that this probability is equal to 0. So the only case that interests me is the case where x is strictly positive. Okay? And keep in mind that what I know is the fact that u follows the uniform on the interval 0, 1. So the idea is that I know the distribution function of u, and I want to be able to use it in order to obtain this quantity here, that is the distribution function of z. So how to continue the computation here in order to make appear the probability that u is less than some 1? I can take the logarithm, in fact. Okay? So if I am on the case where x is strictly positive, okay, so I am here, I have the exponential, excuse me, the logarithm defined this way. That is the inverse of the exponential on r plus star, okay? The exponential being this one, okay? And I know that when x is strictly positive, to say that the exponential is less than small x, exactly the same thing then to say that u is less than the logarithm of x, because the logarithm is the inverse of the exponential and is strictly increasing. It's a strictly increasing mapping. Okay? So it means that now I am able to express the distribution function of z in terms of the distribution function of u. Okay, so now for the moment I don't have used the fact that u is a uniform on the interval 0, 1, we are going to use this fact. Okay? What is the distribution function of a uniform on the interval 0, 1? I can plot it. What is, I repeat, the distribution function of a uniform on the interval 0, 1? Something we have seen together. So, you have it here. It was here, okay, but it was 0 before, okay, the lower bound of the interval, 1 after, and the line between both, okay? And here, in the case of the uniform on the interval 0, 1, the line is just the identity mapping on 0, 1, okay? And you take the formula you have in blue on the slide, okay, with b equal to 1 and a equal to 0, and you obtain exactly this one. So in fact, so I know this one, and here I will have several possibilities depending on the fact that the logarithm may be there, the logarithm may be there, or may be there. So I have three cases to consider, okay, in terms of position of the logarithm in order to be able to compute the distribution function of u at the point the logarithm of x. So I said that when the logarithm here fulfills this, 0. Okay, so 0 if the logarithm of x is negative. Okay? Because I am in this part here. Okay? Now, if the logarithm is between 0 and 1, okay, this is just equal to the logarithm itself. I can put it straight because I have continuity here. Let's write it this way. And what happened in the other case? If the logarithm is greater than 1, my value is 1. Now the only thing I have to do, you see that my conditions here are in terms of logarithm of x, but we are going to express everything in terms of x itself. Okay? So if I summarize what I have obtained here, I am interested in the distribution function of z at the point x. Okay. What is this condition here? When the logarithm is less than 0, that is this part of the curve. Okay? That is when x less than 1. Okay? I am in this part of the curve. The logarithm is negative if x is less than 1. Okay? And of course, that's strictly positive, but I am in this case, the case where I am strictly positive. Here, I am between 0 and 1 if x is strictly greater than 1, strictly less than e. And here, the logarithm of x is greater than 1 if x is greater than e, that is exponential of 1. Okay. And if I summarize what I have obtained here, so 0 if x negative and 0 if x less than 1, that I can summarize as 0 if x less than 1. Okay. Logarithm of x if x strictly greater than 1, strictly less than e, and 1 if x is greater than e. And now I have my distribution function. In order to find what is the associative probability density function, I can apply proposition 12. Here I see that I have something that is continuous, that is in fact very regular, except maybe at 1 and at e, because you have the logarithm that is of class C infinity, and you have constant, okay, in other cases. So I may have two problems at the point 1 and the point e, but it's not my problem, because I can use this proposition, and to use this proposition I don't mind about a finite number of points. Okay? So it means that now if I want to compute the density function related to this distribution function, applying the proposition 12, I obtain what? That the density function of z is the derivative of this mapping. Okay, so 0, 0, 1 over x. Okay. And we have this density function for z that is obtained computing the derivative of this one through the proposition 12. Okay? So it's not a classical distribution, but whatever. I see that here the only thing that I have used in order to compute this kind of distribution function is to use the properties of what? Of the inverse of the exponential. I am interested in the exponential of u. Okay? The mapping that will help me to do all the things here is simply the logarithm that is the inverse of the exponential. Okay? And it means that if I change exponential by a mapping that fulfills some particular properties, that is here to be bijective, to be here strictly increasing, okay, I may find analogous results, okay. And here you have a general methodology that can be applied, okay. Here it involves the logarithm because I start from the exponential, but if I change my initial mapping, okay, the reasoning is more or less the same, okay. Do you have some questions? So what I defined by log, okay, you can also use ln, it doesn't matter, okay, just the inverse of the exponential, okay, the one that I have plotted here. At 1 it's 0, at e it's 1, okay, the inverse of the classical exponential mapping. Do you have some question concerning this? So it was the little exercise I have said to you. So just I won't enter into the details of this proposition because it's exactly what I have done here. Here I have said, okay, I do a particular example with exponential. What I use concerning the exponential here, concretely, I have used the fact that it is bijective and that its inverse is strictly increasing to write this equality. Okay? And I have focused on the points where, okay, I can use the logarithm. It is possible to state a general proposition concerning these topics, that is this one. To me, and that's why I won't spend time on this proposition, I prefer you to be able to do this by yourself instead of learning stupidly this formula. Okay? Because but you can do mistakes when you learn, okay? You won't have the documents for the midterm and for the final, okay? And really I prefer you to be able to do this, okay? If I change my exponential into another thing, okay, you are able to do exactly the same. I have done the job also for the square, okay, together. So you have a proposition. If you want, you can apply. No problem, because it is in the course. But I prefer you to be able to do directly the things, okay, instead of learning this formula. But if you want to learn and if you want to apply, so for example, a good exercise to do at home is to use this one in order to do my previous question. You are going to take in the proposition 14, so x will be a uniform, okay? You will take for j the exponential, j minus 1 will be the logarithm, and you will do the job, and you will find that the density you obtain from this formula is exactly the one I have obtained this way. Okay? But I won't do the job. Okay? So try to do, if you want to apply and to learn it, okay, do. But if you want to apply, okay, tell me all the hypotheses I do in order to be able to apply this proposition. Okay, here you have to do nothing, just know things about logarithm. Okay, so if you want to apply this formula, check that all these statements are okay before to be able to do. Okay? And I repeat that a good exercise, if you want to handle this proposition 14, is to apply it in order to solve the previous proposition we have and the previous example we have seen together. Okay? I won't say more. Maybe just one little remark, and after I will start by doing exercise today. So we are going to start the list 5 of exercise. Just concerning the independence, in fact. So may I erase what I have written on the blackboard? It's okay? Well, it is more than, it is just, in fact, more 2 remarks than 2 new things, okay? So, I just remind you what we have already done together. So, if I have two random variables, okay, I have defined the notion of independence for this random variable. Okay, in this way, x and y are independent if and only if the probability that x belongs to A intersected y belongs to B is equal to the product of the associated probabilities, where A and B are subset of the real numbers. Okay? So it's the general definition of independence we have seen, okay, at the beginning of the course concerning random variable. It's just a definition that extends the notion of independence for sets. So if I want to use words, I can say that 2 random variables will be independent if all the associated pre-images are independent in the sense of sets. That is, the probability of the intersection is equal to the product of the probabilities. Okay? In the discrete case, okay, we were able to transform a little this equivalent definition, saying that if I am in the discrete case, that is in the case where capital X and capital Y take a number of possible values that is at most countable, okay, this independence condition may be expressed equivalently using the fact that independence will be equivalent to the fact that the probability mass function of the pair is equal to the product of the probability mass function of each component, meaning that instead of considering all possible pre-images, okay, I just consider pre-images of singletons, okay, that will give me the probability mass function. So it's something that we have already seen together, okay. You don't seem to be okay with this, okay. So it was this one maybe, okay. Discrete random variables. Tac, 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 tac. No, before. Here. Okay. For the independence, you replace the general pre-images, okay, by, in fact, pre-image of points, okay, and you obtain here, I can say that I have the independence in the discrete case if the probability mass function of the pair xy is equal to the product of the probability mass function of each component, okay. Another result we have seen together in the discrete case is to say that when I have two random variables that are independent, if I take any mapping of x and any mapping of y, okay, I preserve the independence. So for example, if x and y are independent, x squared and exponential of y will be independent. Okay? Any functions that you can make from x and y will be also independent from this definition. Okay? The only little remark that I want to do in the continuous case is exactly the same. That is this one. Okay? So just be careful, because in the continuous case, I can't speak about probability mass function, because I know that the probability that x is equal to a number is always 0. The probability that y is equal to a number is always 0. Okay? But one way to do is to use, in some sense, okay, the distribution function. Okay? So if you compute this kind of probability, the probability that x is less than small x and y less than small y, so something that is a little bit more restrictive than this one, it means that to obtain this one here, it means that I consider for capital A the interval minus infinity x, here capital B the interval minus infinity y. If I replace here, okay, I obtain for this term the distribution function of x at the point small x, and here the distribution function of y at the point small x. If you prove that the probability of this intersection is equal to the product of the associated distribution function, you will have the independence in the continuous case. Okay, so in the continuous case, I won't use probability mass function because all of them are equal to 0. But I have this equivalent way to describe independence. But you will see in a few minutes that in fact it's not this one that we are going to use practically. Practically, we are going to handle density function and see what happens. But for the moment, I have this one. Okay? And we have exactly the same result as the one we obtained in the discrete case. That is, okay, if I have x and y that are independent, you take any function of x and any function of y, they will be independent. Okay? So for example, x squared, okay, logarithm of y will be independent if they are well defined, and if I suppose that x and y are independent. Okay? So there are nothing new. In fact, I don't change, of course, the definition of the independence in the continuous case. Okay? And I obtain the same kind of proposition related to what happens if I start from independent random variable and if I take mappings of these random variables. If I start with independence, I will continue with independence. Okay? So I don't say more for the moment, and we are going to do exercise, and I will continue the course after the break. So it's the list 5 of exercise, and we are going to do 2, 3, and 4 today. 2, 3, and 4. Okay, so I'll try to. Two, three, 4. Okay? the exercise 2 is a result that we have obtained. Okay, not exactly the same one, but in the same spirit than the one we have obtained for which distribution in the discrete case? The geometric. Okay? And I have said to you that I can deduce from this one that the geometric is something that is memoryless, in particular something that can be used in order to model the lifetime of someone or the lifetime of a car, okay, because it's a kind of memoryless property that is defined through this equality. So now what we are going to do, but just to compute exactly the same thing in the case of the exponential. Just a remark, in the case of the exponential, okay, I had to be careful concerning the fact that the inequality are strict or not. Here, keep in mind that in the continuous case, I don't mind about this, because the probability to be equal to 1 point is always 0. So you can have strict, greater than, it doesn't matter. Okay, so for you, it changed nothing. While in the discrete case, it's very important, because in the discrete case, if you add 1 point, okay, and if it is one possible value, then you change the value of your probability. But here, I don't mind about the fact that here I have strict or large inequality, because it gives rise to exactly the same result. Okay? Because x follows an exponential of parameter lambda. Probability that x take a particular value is 0. Okay? Okay, so if you have understood what I have done in the case of the geometric, it's exactly the same here. So I consider that x follows an exponential of parameter lambda. So what is the definition of x? Or what is the way to characterize this distribution here? Or in other words, what is its density function here? What is the density function of an exponential of parameter lambda? So I have lambda exponential minus lambda x, and I don't have to forget that this is the case when x is positive. Okay, so I have an indicator function here. Indicator function x positive. This is the density function of an exponential of parameter lambda. It don't seem to be okay. Like this. That's what we have seen together. So, because I have put strict here, but whatever, you can, in fact, I can put a strict or large, it gives rise to exactly the same thing, because point doesn't matter. But if you be exactly the same than the one I have written in the course, put strict, okay, but of course, I repeat that it changed nothing, because points doesn't matter in the case of continuous random variable. So I have my density function here. Okay. Now I am interested in proving that the equality of the exercise 2 holds. That is this one. Okay. For x and y that are positive. An idea? I repeat, it's exactly the same way we have done the job for the geometric. Exactly. Okay? it's not necessary to have a look on what I have done in the case of the geometry. Just have a look on what you want to do. You want to prove that you have a conditional probability that is equal to this one. Okay? So what is the first thing you can use? You have a conditional probability to compute. I come back to the definition of the conditional probability. Okay? Bias formula. I don't have such a formula explicitly in the course. Okay? But you have just the definition of conditional probability here. Probability of A given B. So if I am interested in the probability that X is strictly greater than X plus Y given X greater than X, it's what? The probability of the intersection. P of A given B is the probability of the intersection. Over the probability that X is greater than small x. Okay? Definition of conditional probability. Probability of the intersection over the probability of. What happened for the numerator here? X and Y are positive, but whatever. X and Y are positive, so what can I say about this intersection here? I am in this simulation here. I have X, and I have X plus Y, because Y is positive. So they may be equal, but whatever, okay? They are always in this kind of order in the large sense. So it means that if I am greater than X plus Y, I am greater than X. So it means that this one is included in this one. So if I take the intersection, it's the smallest in the sense of inclusion. Okay? So this is equal to what? So if I am greater than X plus Y and greater than X, it just means that I am greater in fact than X plus Y. Okay. And I have handled what I have to handle, okay, and I see that if I want to compute this conditional probability, I have to compute this ratio and prove that this ratio is equal to this one here. Maybe, yes, there is a little misprint in the statement here. Where? Here. No, not plus one. I have just here. I need to find Y, I think, here. Okay? Be careful in the exercise 2 here. It's Y, but we are going to do the job and you are going to see what we obtain at the end, okay? And I see that here I will have the X that will disappear and I will obtain a Y here. Okay? Not an X. But let's see, okay? Imagine that you have a misprint, okay? We are going to try to compute. In any case, I see that I need to compute the probability that X is greater than some 1. And after I will see what I will obtain, okay? So it's exactly what we are going to do. For an exponential of parameter lambda, my job, if I want to obtain this one as this one or modification of this one, okay? I am interested in any case to the probability that X is greater than Z, okay, for Z that is strictly positive, okay, or greater than 0, whatever. So how to compute? I know that X is an exponential of parameter lambda. So how to compute this? From the density. So if you want, okay, you have several possibilities. You can write 1 minus the probability that X is less than Z, okay? and you make appear the distribution function, and you know, since you have the density, that in this situation you obtain this one. Okay, write it this way. Okay. I write the probability that I am greater, strictly greater, as 1 minus the probability to be less, and the definition of being a continuous random variable with this density means that my distribution function is given by the integral depending on the upper bound. I can also check directly that this difference may be written as the integral. So I want the probability to be strictly greater than z, or greater, whatever. It's the integral between z and plus infinity of the density function. It's exactly the same here that I obtained. Okay?
My question is, because it's continuous, we can directly use this one, right?
Because it is
Continuous, so
I use continuity, the fact. So I use continuity. I use here the fact that it has a density function.
yeah, I mean, from the density function, we can directly get this one, right? Because it's from the positive infinite to the z, we can directly get from this.
No, it's because by definition of what is the density here. Okay, just this one is this one by definition of what is to have a density. Okay.
Oh, okay.
I define, okay, for capital X to have a density function, the fact that my distribution function is given by the integral from minus infinity to x of the density. Exactly what I have written here. Okay. Of course, in the case of my exponential here, I will know that my density is 0 for x negative. Okay, so in fact my integral won't be an integral from minus infinity to z, but only from 0 to z, but I will see in the second step. Okay. What I have written here, okay, is always true when x has a density function. Okay. So keep in mind that you have the definition, and I have always show you that it's something that I have written not in the slides, but that I have written in the course, is the fact that if I want to express this kind of probability, it is just the integral between a and b of the density function, simply, using the shallow relation for integrals. So I have just used the definition, and I have this one. So it means that I have an integral to compute. Okay, and you will see that in the case of continuous random variable having densities, okay, we are going to compute integrals. Okay. So what is this? But for the moment, I need to use the fact that I have an exponential. Okay, my z is positive. Okay, so I have something here that is a subset of R plus. So on this subset, the density is given by lambda exponential minus lambda x, because I check the condition for the indicator function. So here, it's integral from z to plus infinity of lambda exponential minus lambda x dx. And here, implicitly, I use the fact that my z is positive. If z is not, I don't have such a thing. Okay. If z is negative, okay, I will have 0 instead of z here. Okay. And now to compute this. Well, it's the easy case where I have a primitive for what I have inside. What is a primitive for this one? Minus exponential minus lambda x. Okay, so I have just to take the primitive, that is minus exponential minus lambda x. I have to take this primitive using the notation of my little document concerning integrals in the course between plus infinity and z here. So what is the limit of this one when x goes to plus infinity? Zero. Yeah. Because I have a negative exponential, my lambda is strictly positive, so in plus infinity this one is 0. And I have minus, so it's just exponential minus 1. I am in the easy situation where in order to compute an integral here, I know the primitive basically, so I compute easily the integral. In the discrete case, I computed sums. In the case with density function, I will compute integrals. So I have this one, so I can plug now what I have obtained. The probability that x is strictly greater than x plus y over the probability that x is greater than x. I do the job. Exponential minus lambda x plus y over the exponential minus lambda x. I have simplification. That is just exponential minus lambda y. So if I come back to my statement, so yes, there is a little misprint, okay. Which one? The fact that this ratio here, this conditional probability, obtained to be equal to this red part here, is exponential minus lambda y. That is what? Exponential minus lambda y. That is just the probability that x is strictly greater than y. Okay, so in the statement here, just replace my x here by y. Another way should be possible would be to replace this x here by y. It works also. Let's do this. Okay? And I see that my exponential fulfills the same type of property as the one fulfilled by the geometric in the discrete case. That is the probability to be greater than x plus y, knowing that I am greater than x is just the probability that I am greater than y. Okay? Right?
How can we interpret this to see that, for example, in the geometric case, it is
Right.
largely linear?
Right, it's exactly the same thing here in the case of the exponential. So it means that intuitively that we say this kind of property, the fact that the exponential is memoryless. Memoryless. And what is the meaning of this one? Just a little picture. I have 0, y, let's say this one, and x plus y. So the probability that I am greater than y is the probability to be greater than this number. And the other probability, the conditional probability, is knowing the fact that I am greater than x, the probability that I will be greater than x plus y. So you see that you have a translation of this by small x. Okay? So imagine that if you consider that x is the number of miles you are able to drive your car. Okay? Without any problems, technical problems. Okay? So, let's take, I don't know, y equal 1,000 miles. Okay? And x equal to 10,000 miles. So, if you have a car that is a new one, but the probability to be greater than 1,000 miles, okay, will be a huge number. Okay, at the beginning, okay, the probability that you are able to drive at least 1,000 miles, okay, something that would be very big. But if you suppose that x is big, very big, okay, the probability, I don't know, to pass from 10 to 11,000 miles, okay, will be necessarily less because you have, how to say, English obsolescence. It works in there. Obsolescence. So it means that these kind of probabilities, the same all for the geometric and the exponential, you can't use them in order to model the lifetime of something that may be a human, a car, okay, an animal, something that you want, okay, that becomes in some sense older and older with time. Okay, so it's this property that we call memoryless. Okay.
I have a question about this one.
Yeah.
If the probability the p omega is always equal to 1,
If what? I don't understand. Excuse me. Repeat.
the p omega always equal to 1,
P omega. Who is omega here?
it's a probability space.
Yeah. So P. No, it's not probability space. And P omega is the universal.
Oh yeah,
Okay. So P of omega is equal to 1. Yes, for sure. It's the definition of a probability. Yeah.
we can always get this the one minus this one equal to this one. Why we do not use the definition of this? It's a special case, not p omega not.
No. If you want, it's a special case if you want, but yeah, I just use that P of A plus P of A complementary is equal to 1.
Yeah, I think that's it.
Yeah, you have it for sure. You have a set, and it's complementary set. If you do the probability, the sum of the probability of these two, you obtain one. It's exactly you have here. This is the complementary set of this one here. So this is always true, always in the discrete, in the continuous, and any kind of case.
The question is why we do not use this one for the definition. We use the
For this one?
Yeah.
Oh, it's not my definition.
Yeah.
I can use what I want. Okay, I just say that in my definition of having a density, it's the way I express it. I express it in terms of distribution function. But I have said to you during the course, so it's not written on the slide, but I remind that it is a remark I have given to you that if you want to compute all these terms here, you will be able to compute them as integrals of the density between the boundaries of the interval you are interested in. Okay, so
the question is exists a special case we cannot use this one. We must use the
which one? This?
Yeah,
in the case where you know that you have a density function, you can always use it. Always. So repeat your question in order to make it clearer, and my answer will be clearer also.
It's like it exists a special case that the p omega do not equal to 1.
No. Of course not. I can come back to the very beginning, but okay. So I will take 1 second to do this. Okay. No p of omega is always equal to 1. Okay.
So
it's my definition.
So from the definition, the p.
It's the first thing we have seen together during the first slide.
Okay. No, about that. And the probability is x greater than z can directly from the definition, right? The red come from the integral from the positive.
Excuse me, I don't understand. So are you? Your question is concerning this one?
No.
This one or this one?
Yeah.
I think I understood the question.
But if you understand better than me, can you explain to me, please?
I think he's asking why we use this intermediate step.
Because she told me this remark, so I write it because it was okay.
Okay, but we can.
Because in general, you know the distribution function. Okay? And here it's not exactly the distribution function, but of course you can write directly this one and use this one directly for sure. It works every time for sure. It's just that when I said what is this, I remind that she said this one and I write because it was okay.
So no special case, always works.
It's not, it works. Okay, so this one always works. It's the consequence of this formula. And then when I use density function, it's because I have a density function. So when you have a density function, you can always write this one here. Always. Okay? Always. In the case where capital X has a density function. So thank you for this translation. It's with the mask. Okay? So it's better to be clear. So P of omega is always 1. Okay? Always in the case. It's the part of the definition of what is a probability. Okay? Okay, so I have done the job. Okay? Concerning the fact that for an exponential I fulfill this relation, and the idea was just to compute this kind of integral. Easy to compute them because I have a density function and a density function related to a mapping with a very well-known primitive. Okay? Okay, exercise 3, again a misprint. It's the list of exercise with the misprints here. I don't have a U in my statement here, okay, so it will be just x1 here. Okay, it's a uniform on the interval 0, 1, but I don't have a U in my statement, so just call it x1, this one. Okay. So I consider x1, xn that are, so IID, what is the meaning of this one? Independent and identically distributed. So they are independent random variables with the same distribution, the distribution of all of them being a uniform on the interval 0, 1. Okay? So you have here n independent uniform on the interval 0, 1. Okay? Let y and z be the minimum, all of them, and the max. I have two questions, one concerning y and z, and y concerning the inverse of one of them, in fact, 1 of x1, you can write it here, not 1 over u. If you want to conserve 1 over u, just suppose that u follows the uniform on the interval 0, 1, or if you want to cope with my notation, take just 1 over x1, or 1 over x2, or 1 over any xi, because they have the same distribution. So if you have understood, okay, the first question here is typically what I have done, exactly the same thing that I have done in the case of exponential of the square. Okay, you have just not new transform of capital U or capital X. So may I erase this? Okay. So I have independent uniform on the interval 0, 1, and I am interested in random variables that are built from this independent uniform on the interval 0, 1. The first one being just the inverse. Okay? So I consider V, so x1 with exercise 3 of the list 5. I have x1, xn that are independent uniform on the interval 0, 1. Okay. First question, I am interested in V that is equal to 1 over xn. Now just one remark when I do this. Okay? So in general, when you take the inverse of someone, okay, you take care about the fact that this someone is not 0. Okay? Because you want to take the inverse. So is it possible for me to take this? And if yes, why? X1 can be equal to 0. It's possible for capital X1 to be equal to 0, but I know that. What is the probability that x1 is equal to 0?
0.
It's 0. So from the point of view of probabilities, I don't mind. This case doesn't exist for me because the probability to occur is 0. Okay, so when you do probability, you don't mind about events or set with probability equal to 0. It's like they doesn't exist for you. Okay, so it means that here I take the inverse. Why I have the right to take the inverse? Because I know that the probability that I am, that my denominator is equal to 0 is 0, so it doesn't exist from the point of view of probabilities. Okay? It was just a remark concerning the fact that V is well defined here. Okay? V is well defined. Okay. So I want to find the density of V. What can I do? What can I do? So I have already done the job at least 2 times. Okay. I have already spent, okay, at least 10 minutes in the previous session explaining this. So, I just repeat one thing, that is, for continuous random variable, the probability that I take one particular value is 0.
Yeah, I think the question is why didn't you apply it well defined?
Well defined. Huh? In this case here,
Yeah.
I just say that in general, when you have a ratio, you have to be careful concerning the fact that you don't want to divide by 0. Okay? I just said it, that the probability that my denominator is 0 is 0. I don't mind. It's something that is really different because, okay, if you do classical analysis, okay, so I don't know if you are in the course of optimization with Mr. Bonisso, okay, if you write this, x has to be different from 0, for sure, okay? You know that the mapping has particular values depending on the fact that I am strictly positive or strictly negative, but that is not defined for x equal to 0. Here, of course, it's the same. I don't create new rules of algebra, but the fact is that here, x1 is a random variable, and the probability that it takes the value 0 is 0, so I can always write this, because the case 1 over 0 never happens from the point of view of probabilities. Okay? So, I want V. I want the density of V. So we are going to use this kind of proposition once again. So I know what is the distribution function of x1, x2, xn because they are uniform on the interval 0, 1. And we are going to try to express the distribution function of V in terms of the 1 of x1 and see what happens. Okay? So I am interested in f v of x, that is the probability that v is less than small x, that is the probability that 1 over x1 is less than small x. Okay? And you, as you have understood, okay, we are going to take into account the cases where I am able to say directly that the probability is 0 or 1. What is the set of the possible values for V? So x1 is a uniform on the interval 0, 1. Means that it takes values in the interval 0, 1 with proba 1. If you do the inverse of a number between 0 and 1, you obtain something that is between. So V of omega is 1 plus infinity. The uniform take all the possible values in the interval 0, 1. The inverse will take all the possible values in. It's just from the fact that if I plot the mapping 1 over x, you obtain something like this. Okay? And with this one here, you have 1. Well, it's a very bad picture, but you have 1 and 1 here. Okay? So if you are between 0 and 1, you take all the values between 1 and plus infinity. Okay? So what can I say? There is one case here, or one particular subcase where it's very easy to compute this. If I write, no, this one is okay. But I said that you have to be careful concerning. This one, so be careful concerning this. Okay? It's this inequality that may or you may have a problem. Yeah. If you don't consider cases. Because have a look. If I take the inverse mapping, okay? So I just have to be careful because I have two parts in the inverse mapping, the part where I am here and the part where I am here, okay? So you have to distinguish between the cases. Hmm? The case where x is positive or not, you can tell later here. I'll repeat. Or you have to say, it's not that you have to distinguish, but you have to say one thing, okay? If I have A less than B, okay? Are you okay with this? Are you okay with this? I am not. No, it's not true, this. If I take, for example, A equal to -2 and B equal to 1, of course 1 is greater than -2, but I have here 1 that is not less than -1/2. So, just to say that you need both to have the same sign. So if you want to write correctly what you have written now on your paper, you have to suppose that x is positive also. So you have to consider two cases. The case where x is negative, 0, directly. The case where x is positive, you can use the inequality you write. So be careful, it's not always true here. It's true when I am on this part of the curve or this part. If you take 1 point here, 1 point here, it doesn't work. Okay? The inverse function is not a decreasing one everywhere because it's not defined at 0. Be careful. Okay. But now, since I have remarked this, I can say that this one, when it is equal to 0, x is equal to 1. Okay? Because I know that 1 over x1 take values in 1 plus infinity. So the probability that it will be less than minimal value it can take is 0. And now, okay, now I am in the case where x is always positive, okay? Now I can use the fact that the probability of this, I can use the fact that a less than b is equivalent to 1 over a greater than 1 over b. Because I am in this part of the curve here, okay? So if x is strictly greater than 1, it's the probability that x1 is greater than 1 over x. Okay? Because I take the inverse here, and for the inverse I have a decreasing mapping. It remains to compute this. Okay? So, you can do, listen to me. Excuse me, I don't remember your name, but here it's exactly what I have said previously.
Yeah.
You can do what you want. You can use directly, okay, integral and so on, okay? But it's not the way I will do. Why it's not the way I will do? Because I know the distribution function of a uniform on the interval 0, 1, okay? I know that my uniform on the interval 0, 1 has a distribution function that is equal. It's a picture that I have already done. Okay? It's this picture here. This one, identity 1. Okay? So that's why I will make it this one appear. But if you want to compute with this integral, you just have to be careful because maybe you will have to consider cases depending on the position of 1 over x. Okay? Repeat, you can always write this. So density of V, or excuse me, x1, you can always write this one, but be careful because depending on the value of u, I have particular value for the density. The density is 0 if u doesn't belong to the interval 0, 1, and it's equal to 1 otherwise. So be careful. This one, you can always write it. If you want to develop, be careful. So that's why I will do directly the job, okay? So I don't write this, but you can do, and you obtain, of course, the same result here. I just write 1 minus the probability that x1 is less than 1 over x, and use the fact that I know the distribution function of x1, that is this one. Okay? So I am in this case, the case where x is greater than 1, and I am interested in the probability that x1 is less than 1 over x. Okay, and x is greater than 1. So where I am here, so where I am, x is greater than 1, strictly. Okay, so I am here, implying that my 1 over x is here. Okay? So I am in this part of the curve. I am between 0 and 1. If x is strictly greater than 1, 1 over x is between 0 and 1. That is the case where the distribution function of my uniform is equal to the identity. Okay? You agree? I have this. I repeat why I have this, because I have plot in green here the distribution function of my uniform. Okay? And I know that it's the distribution function of a uniform at the point 1 over x, since I am in the case where x is strictly greater than 1 over x is here. So it's the part where the distribution function is equal to identity. Okay? Okay? Now it's finished. But because I have done the job, I have the distribution function. Okay? So be careful, huh? It should be possible to have different situations. Here, I am always here. That's why I can do the job. But in general, when you do this, you have to consider cases and be careful about these cases. So, I have a distribution function here. I can use the proposition 12. I obtain something that is continuous. Continuous 0 is continuous. 1 minus 1 over x is continuous. And for x equal to 1, both coincide. Okay. And I have something that is very regular because you have a constant here and here, 1 minus 1 over x. So if I want to obtain the density, I just have to compute the derivative here. And I obtain what? So the derivative of 1 over x is minus 1 over 1, minus 1 over x squared. Okay, so at the end, computing this derivative, I obtain, for the density function of v at the point x, I obtain 1 over x squared, indicator function of x. This one. It's the density function of the inverse of a uniform on the interval 0, 1. How I obtain it computing the derivative of this one. 0 here and here. The derivative of this one that gives me exactly this one if x is strictly greater than 1. Okay? So this is the density function of the inverse of a uniform. Okay, it's not a classical distribution, but you have this one. And then here I keep in mind that this one is due to the fact that if x is strictly greater than 1, 1 over x is here. And so the distribution function of a uniform at this point is equal to identity. Okay? Do you agree with what I have written? Okay? So I have the density of the inverse of, so once again, if you want, it's a result that I don't want to use, but you can use this one with my uniform. Okay, the proposition 14, I have said to you that I don't want you to learn, but if you want to learn it, absolutely, you can use, okay, this result with x that follow a uniform on the interval 0, 1, and for j you take the inverse, and you can apply this formula, and you will see that you will obtain exactly the same thing here. Okay? Whatever. So, if you remind an exercise we have already done together, now in the second question of the exercise 3, I am interested in the minimum and the maximum. Okay, so I have independent uniform on the interval 0, 1. Now I am interested in the minimum of all of them and the maximum of all of them. Okay? We have already done and repeat an exercise concerning this topic. Okay? In the discrete case. And do you remind what I have said when you have minimum and maximum? I have said to you that when I was in the discrete case, I have said that it's very difficult to compute the probability that the maximum take a particular value. Okay, so in general I don't do this, the same for the minimum, but I can consider the probability that the maximum is less than, because it will be easier to compute, or the probability that the minimum is greater than. Okay, it's exactly what we have to do in this exercise here. So I will do one of the two. What do you want me to do, the minimum or the maximum? Minimum. Okay? I will do the minimum, you will do the same for the max at home. Okay? So, may I erase the board? Erase. So I am interested in y that is the minimum of n independent uniform on the interval 0, 1, and we are going to be able to find what is the density of this one. So y is the minimum x1, xn. So a priori, if I want to find the density function, the methodology I will use is always the same. That is, okay, this one. I try to find the distribution function and then compute the derivative of the distribution function in order to find its density. Okay? So let's have a look on the distribution function of y. It's the probability that y is less than x. Okay? Where y is the minimum. In general, I don't like to compute this kind of figures. Minimum less than someone, a lot of cases to consider. Okay, because to say the minimum less than 1 means that at least 1 is less. I don't know how to continue with at least. But I can say the following. It's 1 minus the probability that y is really greater. Okay? And now I am happy because minimum strictly greater than x, they are all strictly greater than x, something that is equivalent. The minimum strictly greater than a number means that they are all strictly greater than this number, something that is equivalent. Okay? 1 minus the probability that the mean strictly greater. I repeat that to say that the mean is strictly greater means that they are all. So I have the probability of an intersection. Okay? 1 minus the probability of an intersection. What can I say about the probability of this intersection? I have a statement with hypothesis. I have independence. They are independent. And the fact that they are independent means that the probability of the intersection will be the product of the probabilities. Okay? I have independence about all these random variables. They are independent. So I obtain 1 minus the product from I equal to 1 to n of the probability that xi is strictly greater than x. By independence, I use independence here. Okay? So I have used the independence. I can use the fact that they have the same distribution. They have the same distribution. All of them are uniform, but they have the same. So it means that all these probabilities are equal. Okay? All these proba are equal. So I can write this as 1 minus the probability that x1 is strictly greater than x to the power n. I can write it this way, because all these terms are equal to the probability that x1 is strictly greater than x. And now, the idea is to use the fact that I know x1 follows the uniform on the interval 0, 1. So, I don't know exactly what is this one, but I know the distribution function. Okay? So I write it again. In the case of a uniform, my distribution function is this one, identity 1. Okay? So I can try to express directly this one, or try to express it using the distribution function. Okay, so I can write it this way: 1 minus the probability that x1 is less than small x to the power n. And I have to consider cases. How many cases? 3. Here, here, or here. What are these cases? Okay, the case where x is negative, the case where x is between 0 and 1, and the case where x is greater than 1. So if x is less than 0, what happened? Well, this one is 0, so I have 1 minus 1, that is 0. If x is greater than 1, I have here 1, so 1 minus 1, 0, so 1. Keep in mind that at the end I have to obtain a distribution function, and something with a limit in minus infinity that is 0, limit in plus infinity 1, and so on. Okay, so if you obtain a 0 here, you have done a mistake, for sure. Okay? Or if you obtain 1 here, you have done a mistake. And between both of them, I have what? But I have this one that is x. So I obtain 1 minus x to the power n. Okay? And I see, so I can apply once again my proposition 12. I have here a distribution function that is continuous, because continuous 1 is continuous, 0 is continuous, this one is continuous, and at the possible points of discontinuity, so for x equal to 0, I obtain 0. For x equal to 1, I obtain 1. Okay, so I have something that is continuous here. And except maybe at 0 and 1, I have something that is very regular. If I compute the derivative here, what I obtain, but the derivative will be the density of y, and will be equal to what? Here I compute the derivative, I obtain 0, I obtain 0, and I have to compute the derivative of this one. Okay, so be careful, I have a minus here. So I obtain n 1 minus x n minus 1 indicator function, and write it this way, that x belongs to 0, 1. And you have here the density function of the minimum. Okay, I just compute the derivative of this one. Derivative of this one, that is minus n, I multiply by minus 1 because I have 1 minus x here, and to the power n minus 1, and just take care that I am in the good interval. Okay? So you have here the density function of the minimum n independent uniform on the interval 0, 1. Okay? We'll take for attendance, and after we are going to do break. Okay. Riyad, Arelsan? Yes. Anna, no. Philippe, Bozik, no. Anna Renata, okay. Yuning, okay. Marco, Chengzhang, Eldar, no? No. As usual. Xiaoyi, okay. James, yeah. Excuse me. Ferdinand, okay. Ying, Félix, Patrick, Claudia, Fasika Moulou, yes. An Vuong, okay. Ti Fuong, okay. Kirill, no. Naya, yes. Abhishek, no. Isabelle, she's ill. Send me an email. Don't worry, no COVID, just ill, okay. Because as usual. Bakbergen, okay. Nazari, Yushma, yes. Nasir Usman, okay. Alejandra Maria, okay. Andela, okay. Jelena, Yosra, Sebastian, yes. Sebastian, yeah, excuse me. Jonathan, yeah. Alintak, okay. Yuchen, no. Kayan Céline, no. Yes, me. Zachary, okay. Gil, Nani, Abbas, no. Aisha Aslian, okay. Yueline, Eru, as usual. Okay, so 10-minute break, okay. Someone stay in the room? Yeah.
P 永远都是1的话，它为什么不直接显示这个形式呢？它肯定是为了有什么特殊情况什么的。所以说这个可能不等于1吗？大于错误。
Okay. Yeah. I just wanted to make sure you were safe.
定义的不从正无穷开始，要从负无穷开始。哦，你这个说法也可以。 对，是。但是因为它是 continuous 的嘛，其实无所谓。没有，我刚纠结半天，我以为它会有一个特殊情况，在测度论，如果引入测度的话，它不是那个 P 欧米伽，实际上是概率测度是1嘛？如果它概率测度不是1吗？之类的情况。想想就好可怕。
没到过。
你在国内学过随机过程吗？
我感觉我那个电话的好像那个信没寄到，但现在什么时候收到了？我想要再寄。
要再寄，应该要再寄，应该要再寄。
已经过了快2个星期了。
仇人。
那你看了昨天他发的那个微观的吗？人家没看。
你说那什么，就是期末考试那个，我看了，他第1道题、第2个叫 KKT， 你没看吗？
我就看了。
他第一道题、第2个叫 KKT， 其他都很简单。
就是那个。
对，就直接上 KKT， 然后第3个你说我们还没学什么那个 decision under 什么 risk， 不要 under uncertainty。对啊，不知道就挺迷惑的。但是他也没有别的能说了，因为非让我们证一个那个偏好的那个。
那我觉得那个不用说是能做嘛，没有能做。
我没看一眼。
我最紧张不是除了第2、3个不可以做。
真的有吗？我有点担心。
我以前反正也没有学过第3种，
啥题啊？
他也没给题目是吧？
给题在那个什么上，那个 EPI 上。
哦，这个。
今天已经穿上秋裤了，因为昨天真的冻到我。对，别的上身也。最近是打针？不是，应该不是。我靠，一过来我就冻死了。去市里优衣库啊，去沙村那边优衣库。就沙村那边，你知道沙村那边在哪吗？去老头店旁边，
优衣库
没有，优衣库质量比较好，而且就是有些东西就是亚洲人才穿的，整个优衣库现在。
我感觉还从那个
H&M 就打折的时候超级便宜，不要钱，1欧元一个件 T 恤。说。对，就正常。好像这边没有卖羽绒服的，我忘了，有卖的。反正我上次去在优衣库买的。
优衣库的我羽绒服大概也是
也得5、60欧。我没到哪去。但优衣库质量比较好，比较耐操。不知道这边优衣库好像没有国内那个。
你把凳子带过来。
那不都冻死了？你们还没冻呢？哎，我这里不冷了，正常。别打，你们衣服嘛，那就行。
这样的啊，你没看这道题对吧？你知道 IT 是IT 呢就是但是那个独立的，这个 II。这个
不代表新的前面是你看的某个这个就是相同的，就是他们的分布函数是相同的，他们是同一种啊，但它之间就是相互独立的，相互独立让它的建立。它什么意思呢？首先说独立，对，首先说独立，对吧？独立 SI 独立的，他们。课堂没有讲过了。对，你要看到我就抄了，你看不用再写了。课件两个变量独立的话呢，它就满足这条式它们的概率，对，它们的概率相乘。以前讲过了，这个是加。是变量，是变量。这里很含糊的，他又想用绿色来建模，对吧？又把它变成随机变量的。
我当时问他一个问题，我就很好奇，他不是说那个武汉定义吗？概率空间就给他应该说需要建模概率空间的角色才是一样的，对，它有存在这种特不可思议的情况吗？
你不要让他问这个自动回答，你就把它当成你的选项。每个点对应的函数，这函数是多少？是你定义的。那这跟人是函数有两个人是变的。然后做完了，它就存在测不用，然后它就死活不讲测不。对，我就感觉他如果不讲测不，东西都理不清了。你说你不学测不，这谁会教？这可能不教啊。可能是教学生过程里学习一下，很喜欢这样子。我相信他教程就是他的意思是，我们连续的话，我们是它小于我几个变量是这样。
没关系，
这是一些事情，然后他们两个同时发生的，同时发生的概率呢，其实如果他们是独立的，第一个第二个但是好了，这个也是一样的。对，然后呢，对，使用上加更辛苦。density 大数是对谁？就是没睡觉，没有12点半。density 大数就是这个小白粉，知道小白粉啊，因为它是定义嘛，但是你说什么？这个就是单纯的这个定义它那个，我看一下，在上面。好，首先呢，我们先理解大 S 是什么。首先，先理解这个，先理解这个，我们拿这个来理解，挑一个。我们把这个大 F 的图像画出来。变量的话呢，你到是什么变量 ？S 是
They have to get this.
是 S 是零。我挑一个什么意思呢？这个呢，这个呢，看清楚，这个的意思啊，这个先搞清楚这个意思。这个呢，其实是概率，就是概率，什么概率？
我也很好奇，我主要在我学校有学，他是用你的。
Okay, let's continue, please. Are you okay with what I have written on the blackboard? Can you raise? Yeah? So we are going to do exercise 4 of the list 5, okay? This one. Okay. So I consider a random variable capital X with a distribution function that is continuous, so it's exactly the definition of what is a continuous random variable, one with a distribution function that is continuous, and I suppose a little bit more here than my initial definition. I suppose that I am strictly increasing. That is my distribution function, I suppose it to be strictly increasing. Okay? In the case we have seen together, that are uniform, exponential, and Gaussian. The only situation where I fulfill this condition is which one? Which one has a distribution function that is continuous and strictly increasing? So continuous for the tree, it's okay, by definition of continuous random variable, but which one has a distribution function that is strictly increasing? So if I plot uniform, okay, something that I have already done several times today, let's say the uniform on the interval 0, 1, I obtain, so for the uniform on the interval 0, 1, I have something like this. I am not strictly increasing. I am strictly increasing only in the interval 0, 1. Okay? For the exponential, I have more or less the same kind of thing, because for negative values I am 0, and then, okay, I have something that is strictly increasing. So the only case is the Gaussian one that fulfills this statement here. Okay? Because here you have the uniform on the interval 0, 1. If I plot, for example, the distribution function of because I don't have colors in the room, so I have in my pockets. Okay. If I draw, well, it's not perfect, but something like this, okay? Something like this is the one of the exponential of parameter lambda. Okay? So here again, I am not strictly increasing because negative values are 0, all of them. Okay? And you have the Gaussian. So for the Gaussian, I have said to you that it's not possible for me to have a nice expression, but it's the integral of a density that is always strictly positive depending on the upper bound. So I obtain something that is strictly increasing every time. Okay? I'm not able to have it perfectly, but because I don't know a primitive of exponential minus x squared, let's say, but it will be one case where this result can work. Okay. So before to do the exercise, I just want to show you what are the consequences for f of x if it is continuous and strictly increasing. So when you do analysis, so forget the probability for 1 second here. If you are in a mapping from R into R that is continuous and strictly increasing, what can you say about this mapping? Something that is continuous and strictly increasing. It has one nice property. Not necessarily. You can be continuous, but not necessarily differentiable. It's not totally false what you say, because when you are strictly increasing, you can see that in fact you are not necessarily differentiable everywhere, but the point where you are not are few, let's say. But it's not what I want here. Something that is simpler. So you tell me this. What? Yeah. In fact, that's why I write this in the statement here. It is bijective, in fact. Okay? So when you have a mapping, if you have f that is continuous plus, here I write strictly increasing, but strictly monotonic will work, okay? Strictly monotonic. And you are f is bijective. Bijective on its image, of course. So here, if I take the distribution function, I know that I am from R into 0, 1. Okay? What will be my image in this situation here? The image of f of capital X. So it's a distribution function, so it has some properties, okay? I know the limit in minus infinity, that is 0, the limit in plus infinity, that is 1, okay? And I am strictly increasing, so it means that I never take the value 0 or 1, because I am strictly increasing. If I take one time the value 0, it means that before I am 0. If I take the value 1, it means that after I am 1. And it's not what I want because I am strictly increasing. So it means that I never take the value 0 and 1. They are limits, real limits, okay? So if I want to plot something, okay, I can do this picture. You will have, for example, something like this. Okay? Something, it's a bad picture, okay, but you understand what I mean, okay? My limit in minus infinity would be 0, my limit in plus infinity would be 1, and I am strictly increasing. Okay, so I am not in these situations, okay, because I am not strictly increasing in this situation, but I have something like this. So it means that I can define fx minus 1, okay, fx minus 1, that is something from 0, 1 into R, okay, the inverse. And you know how you are able to obtain it. If I give you the curve of the mapping, if you want to plot its inverse, you just have to take the symmetric with respect to the identity line. Okay, so you do the symmetry. Okay, and if you do it in the correct way, you obtain exactly the curve of the inverse. So I have something like this. Okay, with the classical things that I have fx of x minus 1 of x that is equal to x if x belongs to 0, 1, by definition of the inverse, and fx minus 1 of f of x that is equal to x for all x belonging to R. Okay? It's the inverse, the definition of the inverse. When I do the composition, and I just have to be careful on the set of definition. Okay? When I take into account the set of definition, when I do the composition of a mapping and its inverse, I obtain the identity. Okay? This way. So if I know this, in fact, I have all I need in order to do this little exercise. Keep in mind that continuous plus strictly monotonic, okay, implies bijective in the case of mappings. Okay. So, 2 questions. And typically, from a practical point of view, the second one will be interesting, and I will explain to you just after a while. First question, I want you to prove that if I take fx of capital X, I am able to find the distribution of this one. It is always uniform on the interval 0, 1, always. And what is interesting here is that it's true whatever the distribution of capital X is. If you take the distribution function of X and you compare with capital X, you always find a uniform distribution. Always. Okay? It's the first question I have to solve. Yeah?
Can I ask about like the implication that continuous plus strictly increasing means that the function is bijective?
Yeah.
Why?
It's a result of analysis, so it should be possible for me to give you the proof, but it will be very far from my course of probability.
Just to remember.
Okay, but yes, I just give you this. So typically, if I want to you to use this kind of result in an exam, for example, I will remind you this. Okay, it's what I have done here in some sense, because you have the inverse in the statement. Okay, so it means that the inverse exists, but here, okay. So don't worry, because in general, okay, if my exams are done in a good way, you won't need, okay, to use very particular result of analysis like this one, okay? Of course, you need to know something about computing integrals, computing sums, okay? But it's something that I can't ask you to know perfectly, okay? So that's why if I need it, I will give you a reminder in the statement. Okay. So, what can I do to do this? What can I do? So, in this part of the course, in order, okay, to check if a random variable has a particular distribution or no, I have 2 points of view if I want in the continuous case. I can work with the distribution function, or I can work with density. Okay? But here you see in the statement that you have something that is in relation with distribution function, because, okay, distribution function is the keystone of the statement, in fact. Okay, I have some hypothesis on the distribution function, so it seems to be not that strange, okay, to consider in order to answer to these two questions, okay, to consider the distribution function of the concerned random variable and to see what happened. Okay? So to prove that this one follows the uniform on the interval 0, 1, we are going to try to compute its distribution function and see that it is the same as the one of a uniform on the interval 0, 1. Okay? So may I erase this? Okay. So I am interested in the distribution function of fx capital X. So if I just use the notation of my course, okay, what I am interested in is the distribution function of fx capital X at the point small x, okay, that is just the probability that fx capital X is less than small x. Okay? And the idea is to prove that when I will compute this term, I want to be able to recover exactly the distribution function of a uniform on the interval 0, 1. If I do this, I will prove that my random variable of interest will have this distribution. Okay. So I have to compute this and prove that this number is equal to the distribution function of a uniform on the interval 0, 1. That is what I have plotted in green here. Okay. So I have cases that are not that difficult to compute. Because what? What are the possible values for f capital X of capital X? 0, 1. I am inside the interval 0, 1. So typically, I know what happened. What is this probability in this case? What is the probability in this case? Okay. So, what interests me is the case where I am between these two values. Okay? When I am between these two values. So we have done several exercises of this type. Typically, I have done the job with exponential of capital X, let's say, and we have used what we have used in order to do the job. We have used the inverse of the exponential, that was the logarithm. Okay, it's exactly what we are going to do here. Okay, because what I know that fx is continuous and strictly increasing, so it is bijective. Bijective from R into 0, 1. Okay? So it has an inverse, that is fx minus 1. What can you say about the monotony of fx minus 1? If you have, in other words, if you have a mapping that is increasing and bijective, what can you say about its inverse? Of course it is bijective. So if you have a mapping that is bijective, its inverse is bijective. But if you have a mapping that is bijective and strictly increasing, what can you say about its inverse? It is also strictly increasing. Okay? So meaning that in this situation I can apply the inverse in the inequality and it won't change the side of the inequality. So here I apply, in this situation, fx minus 1, both sides of the inequality, and I repeat, it doesn't change the side of the inequality because fx minus 1 is strictly increasing. So the probability I am interested in may be written as fx minus 1 fx x less than fx minus 1 of x. I just apply fx minus 1 on both sides. Okay? It's what I have done with the logarithm and the exponential, okay? For good situations. So I have to deal with this term here. Okay? I have to deal with this term. And I will handle it here. What can you say about fx minus 1 fx here? It's the identity, okay, by definition of an inverse. So the probability I am interested may be written as the probability that capital X is less than fx minus 1 of small x. Okay? Now, I said that it's finished. In fact, why it's finished? Keep in mind that what I define as f capital X small x is the probability that capital X is less than small x. So you have here the distribution function of capital X at this point. So I can write this as fx minus 1 of small x. And what is this? Small x. So the term I have computed in orange is small x. And what I obtain at the end, I obtain that the distribution function of fx of capital X take these three possible values, that is to be 0 before 1, to be identity between 1 and 0, and to be 1 after 1. What I recognize here is exactly the distribution function of a uniform on the interval 0, 1. So this random variable here has the same distribution as the one of a uniform on the interval 0, 1. So I can conclude that I follows a uniform on the interval 0, 1, because the distribution function characterizes the distribution of a random variable. I repeat, my job was to compute the distribution function of the random variable I am interested in. And using this computation, what I prove at the end, I prove that this distribution function is none other than the one of a uniform on the interval 0, 1. That's why I can deduce that fx of capital X follows a uniform on the interval 0, 1. Okay? So I have answered my question. If you apply to capital X the distribution function of capital X with some hypothesis, I obtain a uniform on the interval 0, 1. Always independently of the initial distribution of capital X. My only hypothesis is that the distribution function is continuous and strictly increasing. Typically, if you do the job for a Gaussian, it will work. Okay? Some questions, maybe? So I repeat that here, it's not that strange to try to compute this quantity, because I see that in my statement, distribution functions are important. Okay, so in order to find what is the distribution of a random variable, let's compute its distribution function instead of doing other things. Okay? That's what I obtained doing this. Do you agree? Yeah, no. Okay? Everybody? I'm not sure that everybody. See your eyes. Make sure that everybody has understood. I apply this, okay. I said this one is bijective, so that's why I can do the job here. Keeping in mind that fx minus 1 is also strictly increasing if f of x is a mapping, okay, that is continuous and strictly increasing as an inverse that is also strictly increasing. Okay. Let's take, for example, the exponential in the logarithm, okay, or the square and the square root on r plus. Okay. So I have done the job. Second question, that is slightly different. I consider a uniform. I apply fx minus 1 and I recover the same distribution as x. That is, okay, I prove that the distribution function of this one is the same as the distribution function of x, in order to prove that in fact fx minus 1 of u and x will have the same distribution. Fx minus 1 of u and x have the same distribution. And in practice, it is this kind of result that we use. So what is the idea here? So I will do the job, it's a little computation, to prove that this one has the same distribution as capital X because fx minus 1 of u has a distribution function that is none other than fx. Okay? So in practice, how I can use this result? Typically, if I give you a capital X fulfilling this hypothesis, and with the inverse of the distribution function that is perfectly known. If you apply it to capital U, you'll be sure that you will have a random variable that has exactly the same distribution as X. So from a computational point of view, if you are able to compute fx minus 1 explicitly, in order to generate this random variable with a computer, it won't be more complicated than to generate uniform on the interval 0, 1. So if you generate uniform on the interval 0, 1, you will just have to apply fx minus 1 to what you have obtained, and then you will be sure to obtain realization of my random variable capital X. Okay. And in general, to generate a uniform on the interval 0, 1, in all the computers you have here, you have a random function that allows you to do this. So just applying fx minus 1 when it is perfectly known will allow you to generate the distribution function or the distribution you want. And typically, even if I have said to you that the Gaussian distribution fulfills this statement, okay, but I don't know fx minus 1 explicitly. But I have very, very good approximation of fx minus 1. And if you know this very, very good approximation, if you apply this very, very good approximation of fx minus 1 to u, you obtain this way realization of a Gaussian distribution. It's one way to generate Gaussian random variable using a computer. It's what we call, okay, if you follow a course that is called Monte Carlo methods, it's the inversion method in order to generate a random variable. You take the distribution function, you try to compute its inverse, you apply a uniform, and you obtain this way a new random variable having the same distribution as capital X. From a practical point of view, it's the way we use this result in general. Okay, so let's prove this little result. So once again, I am interested in fx minus 1 of u. Okay? And I want to prove that it has the same distribution function as x. Okay, so I am interested in the distribution function of what? Of fx minus 1 of u. That is by definition the probability that fx minus 1 of u is less than small x. Okay? I have to compute in one line. The interpretation of this result, okay, is more interesting than to prove it directly. It's not difficult to do. What can I do now? mind that I have some hypotheses. Huh? What can I do in this inequality here? The idea is to make appear this one, okay? So what can I do in my inequality? Yeah, I can apply both sides f capital X, because I know that it is bijective and strictly increasing. So it changes nothing in the side of my inequality. Okay, so this probability is in fact the probability that fx minus 1 of u is less than fx small x. Because fx is bijective and strictly increasing. And now it's finished, more or less, because what can you say about fx compound with fx minus? It's the identity by definition of the inverse. So I obtain the probability that u is less than fx of small x. And I know what is the distribution function of a uniform. I have still the curve in the board here. It's the green one. 0, identity 1. Where is this point here? It's fx of small x. So I have someone that is between 0 and 1. So I am in the part where the distribution function of u is the identity. So this is just the point itself. And at the end, I prove that the distribution function of fx minus 1 of u is exactly the distribution function of x, meaning that this random variable and this one have the same distribution. Okay? It's just a little play using the inverse of the distribution function. And the fact that here, in order to compute this one, I remind what is the distribution function of a uniform. 0, identity 1. Here, this point is between 0 and 1 because it's the distribution function at one point. It's the probability that x is less than small x, this one, so it is between 0 and 1. And so the identity form of the distribution function apply here. And I have proved my result, proving that both the two distribution functions are equal. It's exactly what I want to prove. Here. Okay? So you will see that when you will do finance, okay, sometimes you will have to generate particular distributions in order to do the job. Sometimes you will use this kind of methodology, the second step here in my exercise, that is called the inversion method, okay, to generate particular random variables from a computer. Okay. If you are able to generate a uniform, you will be able to generate, in this situation, okay, the distribution of capital X. Are you okay with my? So I write the definition of the distribution function for this random variable. I apply f of capital X on both sides of the inequality because I have the right, because the inverse exists and I am strictly increasing. Okay, so I have equality between these two sets here. Then I simplify fx and fx minus to obtain p of u less than this number. And now, in order to compute this one, I have just to check where I am on R in order to apply the definition of the distribution function of u. And this point is between 0 and 1, so that's why I have the identity part of the distribution function of u. Okay? So I will continue the exercise next session, okay? I will continue a little the course now. So the objective is to finish the course this week, okay? I don't remind exactly what is the program of the, maybe I need a little bit more for the program of the midterm. I have the moment generating function inside that I will finish next week. So before the holidays, you will have the program of the midterm that will be finished, even if the midterm is November 10. Okay? So during the holidays, if you want to work, you will have the possibility to work for the midterm, okay, without problem. So may I stop with this exercise, or do you have questions? It's okay?
Do you understand one step?
Which one? This one? Okay, so I just say that what you have here, you have the probability that a uniform is less than a point. The probability that a uniform is less than a point is this curve here. 0, identity, 1. So in order to have the value of this probability, I just have to check if I am here, if I am between 0 and 1, or if I am after 1. And I just say that this point is between 0 and 1. So the value of the distribution function of u at this point is equal to the identity that is exactly this point. It's exactly what I have written, this one and this one. Okay? That allow me to conclude that both distribution functions are equal. Okay. Other question, or I may erase? Okay? So I erase and I will continue. So the course. Okay. Before to continue the course, just a little remark. So, it's what we call the Fubini theorem, but I don't want to enter into too much details, just tell you what you are going to be able to do in this course. Okay? When we work with density function, we work with integrals for sure, okay, because you have to integrate mapping depending on one variable. Now we are going to consider, as we have done in the discrete case. In the discrete case, we have seen that, okay, if I start with two discrete random variables, okay, the pair is a discrete random variable, and so I can characterize its distribution by the probability mass function that may be obtained a priori from the distribution of each component. So here we are going to do the same in the case of continuous random variables. So we are going to be interested in pairs of continuous random variables. And you will see that in particular situations, we are going to obtain density for the pair. It's what we call the joint density. And the joint density, since it is related to a pair, but I can do the same for a triple, a quadruple, okay, or an tuple of random variable, you will have a density, or the generalization of the notion of being a density as a mapping depending on several variables. Okay? So I will have to do multiple integrals. Okay? Not just integrating with respect to one random variable, but 2, 3, 4, 5, and so on. And one result you have to keep in mind is that in the case we are going to be, that is what I call under mild condition, that I won't make explicit for you, but typically F positive work, okay? And it will be typically the case where we are going to be, F positive, okay? So in this situation, when you want to compute a double integral, what you have to keep in mind is that you can do what you want. That is, first integrate with respect to x, and then integrate with respect to y, or integrate first with respect to y, and then integrate with respect to x, and you obtain this way exactly the same thing. So it's exactly what I have written here, that the double integral is in fact just computing 2 times an integral, first with respect to x, or with respect to n with respect to y, or the converse. And it gives rise to the same thing. And what I call mild condition will be all the conditions you will be in this course. Okay? So when you will have to compute a double integral, you will have the possibility to use this kind of result. Okay? And this result is called, what I have written here is a very particular case of what we call the Fubini theorem. Fubini was an Italian mathematician, okay, that was interested in, okay, when it is possible, when I have several integrals to compute, but to do the computation in the order I want. For you, it will be every time. Okay? So let's see a little example here. We are going to see several times. Okay, so suppose, it's a little exercise, let's say, I define f of xy this way. Okay? So it is, I'll write it another way. So it is lambda square exponential minus lambda y. Okay? And I have the indicator function of x between 0 and y that I can write this way. Indicator function that x is positive and less than y. Okay? It's exactly what I have written in another way here. I have this. X is between 0 and 1. Okay, it's what I want. My question is, compute this integral. Okay, so the first thing you remark is that I have integrals of things that are positive. Okay? But I have said that the result I have written in blue, you can use it anytime. Okay? Without justifying anything. Okay, so suppose that I want you to compute this. Okay? To know what is the value of the double integral. So, I have said from my previous remark that I can compute the integral in the order I want. First, I can compute the integral with respect to x, and then compute the integral with respect to y. What do you want to do? X or y? It will give rise to the same thing, but sometimes it's clever to do in one side and not the other. So which side you would prefer to do? But I have a kind of dilemma here because, okay, I said that if I first compute the integral with respect to x, okay, I have only this term here. So the integral will be y. Okay, more or less. But then I will have to compute the integral of y exponential minus lambda y. Okay, but I will be able to do this. Okay? The other thing is to say that, okay, but I have a nice mapping here that is an exponential, and I know it's primitive. So I can compute also the integral. So in fact, here, to compute the integral with respect to x or with respect to y first, I give rise to the same thing in terms of complexity. Okay? So I will do the computation with respect to y, me, an atom, do the first computation with respect to x and then with respect to y. But I don't want to use this for the moment because I don't want to do integration by parts. Okay, I will do it just in a few minutes, but not now, okay? So let's compute the integral with respect to y. Okay. What happened for my bounds? Y is greater than x. Okay? It means that in fact I don't have an integral from minus infinity to plus infinity. I have an integral from x to plus infinity. Okay? And in this case, I have this. But I have to be careful if I write this because I miss something if I do this. What I miss? I have lost some information if I do this. I am agreed that y is greater than x, so it's what is translated in my integral here. I integrate for a y that is greater than x, but don't forget that x is positive, So I have to write, if I don't write, I will have a problem after. Okay? I compute this integral, but for an x that is positive. So I have removed this part from the integral because it's an integral with respect to y and I don't have a y here. Okay? So keep in mind that this indicator function is in fact the indicator function of x greater than 0 multiplied by the indicator function of x less than y. I have two indicator functions in fact that I regroup in the same one. And now it's finished because I know a primitive of this one. Which one? I know the primitive of the negative exponential. So I obtain minus lambda exponential minus lambda y that I have to take between x and plus infinity and multiply by the indicator function of x positive. Okay, so the primitive of this one is just minus lambda because I divide by lambda exponential minus lambda y. Okay, that I have to take between plus infinity and x. What is the limit of this one in plus infinity? 0, because I have a negative exponential with lambda that is strictly positive, as written here. My lambda is strictly positive in the slide. So in plus infinity, this term goes to 0, and it remains the other one. That is just lambda exponential minus lambda x, indicator function of x positive. What I recover here, you know what I have obtained here. Yeah, it's the density of an exponential. It's the density of an exponential of parameter lambda. And now, keep in mind what I want to do. I want to compute the double integral of this mapping. I have first done the job with respect to y, and then I have to compute the integral of what I have obtained. Okay? So first, I do the computation with respect to y, and once I have done this computation, I have to integrate with respect to x. But I remark that what I have obtained computing first this integral here is just the density of an exponential of parameter lambda. So what do you obtain if you compute the integral with respect to x? 1. Okay? I obtain 1. Because what I have inside here, the computation of what I have inside tell me the density of an exponential of parameter lambda. When I compute its integral, I obtain for sure 1. Okay? Keep in mind that in this course, since we have defined several density functions, we have several mappings with integral equal to 1. And you are going to see that in order to compute integrals, we are going to use this result a lot of times. Okay? So I have made this choice, okay, but at home, in order to train, okay, you can do the converse. That is, first you compute the integral of this one with respect to x, and then do the computation with respect to y. Okay? You will see that you won't have a classical primitive in the second case, but you will be able to use an integration by parts, or to know a result that we are going to see in a few minutes. That is the expectation of an exponential of parameter lambda. So here you have an example of a mapping that is positive, okay, and with the double integral that is equal to 1, according to the computation I have done. Okay? In fact, typically this kind of mapping will be what I will call in few seconds a joint density function. That is a mapping depending on two variables that is positive, let's say continuous almost everywhere, and with a double integral that is equal to 1. Okay. So are you okay with my computation? And keep in mind that this slide is just to tell you, do what you want when you compute double integrals, that is, compute them in the order you want. Okay? It works. Okay, so a definition that is related with what I have said. Okay. now we are going to work with two random variables. Okay? And I say the following. Two real random variables x and y are jointly continuous if there exists a regular mapping such that the probability that x is less than small x and y is less than small y is equal to the double partial integral of the mapping f small f capital X capital Y, that is called the joint density of the pair. Okay? So if you want, this definition generalize what I have done in the case of 1. In the case of 1, I have this. I am continuous, and I have this density function. If I fulfill this, with this one, that is the probability that capital X is less than small x. If I add a new random variable, I am interested not in the probability that capital X is less than small x, but the probability that x is less than small x and y is less than small y. And in this case, I have a joint density if this equality is fulfilled. Okay, so it's a notion to have a joint density function is a notion that generalizes what happens for a single random variable, but in the case of 2. Okay. So let's have a look on this definition a little. So I erase my computation. So let's see an example here, the one in black here. Suppose that I am in the following situation, okay? I suppose three things. That X has a density that is denoted by F capital X. Density in the previous sense, okay? For a single random variable. I suppose that the same holds for Y. And I suppose them to be independent. Why not? It's my example. Okay? So suppose that they are independent. In fact, we are going to see that the pair xy has a joint density function in the sense of this definition. Why? So if I want to prove that I have a joint density function, I need to check that I have this inequality for a particular mapping here. Okay? So we are going to start from this part, and we are going to see what happened in this particular case. And we are going to see that in this particular case, the joint density will be related to the density of each component here, x and y. So let's see what happened. I am interested in the probability that x is less than small x intersected with y less than small y. What can I use in order to compute this? I have the independence, so the probability of the intersection is equal to the product of the probabilities. Okay? The probability of the intersection is equal to the product of the probabilities. But I know that each of them has a density function. And from the definition to have a density function, that is the definition 17, each of these terms may be expressed using the density function. So if I continue here, I can write this product as a product of two integrals of this type here. Integral minus infinity x, write it this way, fx of u, that is for the first part, this probability, multiplied by the probability that capital Y is less than small y, this one. Okay? So I have the product of two integrals. But according to what I have said, so I am in this situation here. Okay? I have the product of two integrals. this part depending on u, this part depending on v, and in fact, according to my notation in blue, I can write it as a double integral here, in fact. Minus infinity x, integral minus infinity y, of what? Fx u, Fy v, du dv. Because I can separate the term inside, okay? Because I have one part that depends on u, the other part that depends on v, I can separate. And I obtain this, and it's finished because if I come back to my definition, so they are jointly continuous if there exists a regular mapping fulfilling this. It's exactly what I have done here. Okay, and I can see that in this particular case, the joint density is equal to the product of the density of each component. Okay? So I repeat, according to my definition, in my little example, I can say that if I have two random variables having a density that are independent, the joint density function is just equal to the product of the density function of each component this way. Okay? That's exactly what I have written in my little example. But typically, we are here in a very, very particular situation, the case where they are independent. And most of the time, okay, they won't be independent. That's why, in general, the joint density function won't take this form. In general, it won't be possible to separate the joint density function in a part only depending on u and a part only depending on v. You will have inside parts that will depend on u and v at the same times. And you will be the link between this and what we are going to do after the holidays that are, okay, the conditional density function, okay, and the notion of conditional expectation. But in the case, okay, where they have density function and they are independent, I have this. Okay? So I just copy here the definition of having a density function is just the fact that I am able to express this quantity using a double integral of a mapping that I call fxy u. I have this one, okay? Doing the integral in the order I want. Okay, so this proposition will be helpful for what we are going to do. So you have several things here. Three statements. The first one is the analogous of what we have already seen together, that is this proposition, the proposition 12b. The proposition 12b tell you that, okay, if the distribution function is sufficiently regular, to obtain the density, you just have to compute the derivative of the distribution function. But here, in the case of joint density, you will have exactly the same. If I want to obtain the joint density function from this formula, what I have to do? I have integrals depending on the upper bound. Okay? So if I compute the derivative with respect to x, it makes disappear this first integral. If I compute the derivative with respect to y after, it makes disappear the second integral, and it remains what I have inside. So it's exactly what is written here. So if you have this equality that is true, okay, and if I give you a particular form for this term here, you will be sure to obtain the joint density function of the pair xy if you compute, in fact, a second derivative with respect to x first and with respect to y. But keep in mind that I can invert between these two. So it means that first computing the derivative with respect to x or compute the derivative with respect to y, will give rise to the same thing if you change the order of derivation. It's what you do in optimization. It's the Schwartz lemma. The fact that when I have a mapping that is sufficiently regular, when you have to compute second partial derivative, you can do them in the order you want. That's exactly what I have. The only differentiation is that in the optimization course you are fulfilled on the particular hypothesis and check that they are okay. In my course of probability, I will use this result as tools, okay? And it's not my main topic. So is it clear for everybody that if I give you P of x less than small x intersected with y less than small y, that is if I give you this one, if you want to obtain the joint density function, you will have to compute a second derivative. Okay? So it is the first statement. Second statement, if you are jointly continuous, that is, if you have this relation, you have two good news. First, the fact that x itself has a density function, and that y has also a density function. So if the pair has a joint density function, each component has a density function. Be careful, we are not in the framework of my exercise. In the framework of my exercise, I have just said that if they have density, if they are independent, they have a joint density. It's not what I state here. I said that if they have a joint density, each component has a density function. In order to obtain the density function of x, it is sufficient to integrate the joint density with respect to y. In order to have the density of y, you just have to integrate the joint density with respect to x. Okay. So let's prove this. I erase this. It's not complicated to prove. So if you want more details on the proof, you have them okay in the list of proof number 2, my website. So let's do the job for x, and it will be exactly the same for y. So I know that my two random variables are jointly continuous, meaning that I have this inequality here, okay? And I know that I can compute the integral in the order I want. So I can write it this way. Minus infinity x, okay, and then minus infinity y. I have f x y u v. So I can do the job with respect to the second variable here, and here the first variable. I can do the job in the order I want. If I want the density function of x from this relation, in some sense, okay, using proposition 12, I know that if I want the density function, one possibility is to have the density function, excuse me, the distribution function of x, and then to compute its derivative. Okay? In order to find the density function of x, you can first compute its distribution function and then to compute the derivative of the distribution function. Okay? So I am interested in this term. And my question is, do you have an idea how to obtain this one from this one? First, an intuitive idea. If you have also the theoretical result that is below, it will be perfect. But I won't enter into too much details. If you want more details, okay, I will give you all the arguments now. But if you want a little bit more details, go to the list of proof. So how to make disappear the set capital Y is less than small y intuitively? Y, okay, is a random variable taking real values. Okay? And I want to make disappear this event here. Do you have an idea concerning what?
We integrate the value of
reintegrate? You want to integrate this one with respect to what? So you want to compute the integral of this one with respect to small y? So you will have a triple integral to compute. Okay? And what will be the link between? Oh, if I have understood, you will tell me if I have understood what you say. You tell me that, or I have understood that you want to do this. I don't have understood.
So for us to have a density function, we always derive from the mass function, so we just do the inverse. So we just do the integral of capital F.
What is capital F here?
The mass function.
So tell me exactly what you want to do. You have all the names of the function. What do you want to do? You want to integrate someone here?
Yeah, I want to integrate the mass function in order to apply
Which mass function?
of the giant mass function.
Okay, so in fact, what you want to use is, you want to use the result I want to show, in fact. Yes, it's what we are going to obtain. I'm agree with you that intuitively, okay, we have already seen together that to obtain a distribution function, okay, it's to integrate the density, and the density is obtained by differentiating. You agree with this, okay? But here, I said the following. I said that if I have a joint density, okay, I want to prove the fact that the density of each component will be given by partial integrals. Okay? So if you tell me I compute the partial integral and I will obtain the density, I am okay because it's the result we are going to prove, but I want to prove it.
Okay, so then we can just use as we did in the discrete case.
The problem is that we are not in the discrete case.
But you can use the same logic as we did with the.
I am agree with you, but
The joint unit, we can just do the.
okay. So do you remind the argument we have used in the case of the discrete case? What was the name of the theorem we used in the discrete case? Yeah, we used the law of total probability. So I am agree with you that what we are going to say is a kind of equivalent of the law of total probability with respect to all the possible values of y, in fact, of the result we have seen in the discrete case. I am totally okay with this one. The problem is that I don't have a version of the law of total probability in the continuous case. Okay, so if you want, what we are going to try to do will be a kind of proof of an analogous of the law of total probability in the continuous case. But I am agree that this is the intuitive idea here. So have you understood what she said? She said that in the case of the discrete case, I am interested in the probability mass function. And my question was exactly the same as this one, that is how to make disappear this part. The way we make disappear was using the law of total probability, doing the sum over all the possible values of y. And from the law of total probability, I know that this one is this one. Okay? What I want to do is the same thing. The problem is that I don't have the law of total probability in this case, because to have the law of total probability, I need to have a partition of the universe that is countable, and typically in my continuous case, I won't have countable possible values. Okay? So it's a kind of analogous, but with a continuum of possible values. So it's exactly what we are going to do, and in fact, we are going to replace sum by integrals. But my question is how and why I have the right to do. Here, it was a consequence of the law of total probability in this part of the course. Unfortunately, if I change r of y that is countable by an r of y that is not countable, I don't have the law of total probability anymore, because the law of total probability works for a countable partition, and only a countable partition. If I have a partition that is not countable, I can't say anything. Okay? But this is the idea. This is the idea. So keep in mind that y is from R into R. Okay? So, I am sure, it's an intuitive proof that I do, okay? I am sure that if I am in this situation, y is less than what every time? No. No, it's a random variable. It can take all the values you want in the real number here. Okay, it's not the distribution here. The values, the possible values for capital Y. Real numbers, all of them. There is someone you know that is less than all the real numbers. How do you call it? Yeah, plus infinity. Okay, so I don't say that my proof is totally rigorous, but if I put y equal to plus infinity in my, if I have the right to do, I don't say that I have the right, but if I have the right to, I replace the things, and I know that y is always less than plus infinity because I take real values, so this one becomes the universe, so I can drop it from my intersection, and I obtain this. So it means that if I have the right to do this, and I will explain to you just after why in fact I have the right to. If I have the right to do this, it's finished. Because what I proved here, I proved that the distribution function of x can be written as this partial integral. But if you come back to the definition of a density function I have given to you, it was this. If you express the distribution function of x as the integral between minus infinity of x of sum 1, this sum 1 is the density function. But here, my density function is what I have below, this one. Okay? Because I can express the distribution function as the integral between minus infinity and x of this mapping that becomes the density function of x. To obtain the density of x, I just have to compute the partial integral with respect to the second variable. In the same way, if you want the density function of y, you will just have to compute the density and the integral with respect to the first variable. Okay? So my last question is why I have the right to take plus infinity. In fact, I don't have the right to do this. The only thing I can do is to take limits and to make y goes to plus infinity maybe. But we have in the course two results that allow you to invert between limits and probabilities. You have a result that tells you that when you have an increasing family of sets, the limit of the probabilities is the probability of the union. And it's this result that you are going to use in order to prove that, in fact, I can replace y by plus infinity, just taking the limit of this term when y goes to plus infinity. Okay? So I won't enter into too much details. You have the details in the list of proof, but the idea is exactly this one. Why I have the right to replace here by plus infinity? Because I have a result in the course that allow me to invert between probability and limits. And the way to do is to consider a y growing toward plus infinity. Okay? If I admit this, that I have in fact justified, not in all details, but this is the theorem that is below this, okay? I write this equality, and now since I have this equality, I know that in order to find the density function of capital X, I have to compute the derivative of its distribution function. When I compute the derivative of this term, since I have an integral depending on the upper bound, I obtain what I have below. That is exactly this term. Okay? So if I give you a joint density, it's possible to find the density of each component computing partial integrals. Okay? The last result we have seen together. Previously, I have said to you that if they are independent, then The joint density function is the product of the density function of each component. We have done in the previous example here, I have done the proof of from the left to the right. If they are independent, then I have this. But the contrary is simpler to prove. Suppose that you have this, okay? You plug it inside. You have one part that depends on u, one part that depends on v, meaning that you can separate both integral in order to find that the probability that x is less than x intersected with y less than y, it's not an x, it's a y here, is equal to the probability that x is less than x times the probability that y is less than y, and so you have the independence. So the side I have done, okay, is in fact the hardest for the other one. Just plug this relation inside this definition and see that you can express the probability of the intersection as the product of the probabilities. So when you have a joint density function, okay, you can recover it computing a double derivative with respect to the parameters of the this quantity. If I give you a joint density in order to obtain the density of each component, you compute the partial integrals. And here, in the case of continuous random variables that are jointly continuous, you have a very powerful way in order to check if they are independent or not. They will be independent if and only if their joint density is equal to the product of the density of each component. And from now on, okay, in order to prove independence in this case, it's what we are going to use to prove that the joint density may be expressed this way. Okay. So I will just finish by a little computation. I have already started. That is, I come back to my little example with the mapping. I have proved to have an integral, a double integral equal to 1, okay? So in fact, it is a joint density function, and I will just show you what is the density of each component here. It's just a computation of integrals. And next session, okay, in fact, I have two things to deal with. But first, to tell you what is the analogous of expectation, variance, and so on in the case of continuous random variable. Okay, you will see that I just change sums by integrals. All the properties will be the same. Okay, so you won't have to learn more than what you already know, just to adapt to this case. And I have just a little result that is not that simple, but we are going to practice a little next session. That is, okay, for the moment, and I have started to do this in this course today, I said that if I start with a random variable and I transform it, sometimes I am able to tell what is the new density function. In fact, we have the analogous of this result, not for a single random variable, but for pairs of random variables. I start with a pair that have a joint density, I modify it a little, and I have a result that tells me the new pair will have a new joint density that I am able to compute explicitly. Okay? It's what we are going to see next week. So I just want to finish in 2 minutes with this example here. So we have already seen together that if I define this way, if I compute the double integral, okay, I obtain 1. I have done the job. Okay? Now we are going to see that if I tell you that this is the joint density function of a pair, my question is how to find the density function of each component. In order to find the density function of each component, by the statement 2, you have to compute partial integrals. Okay? So, if you compute first the integral with respect to what? So, I have to do both. So, let's do with respect to x. I want to compute the integral with respect to x here. Okay? I can remove the term that doesn't depend on x from the integral, that is this one. And I can also take into account the fact that x is between 0 and y is positive. So I don't have to forget that my y is positive. Okay? And it remains an integral that is just the integral between what and what. But my x is between 0 and y. And I compute this integral. And what is the integral? Just y. Okay? So I see lambda square y exponential minus lambda y indicator function y positive. So you have here the density function of y, the second component. If you suppose that a pair has this joint density function, the density function of the second component will be the integral of the joint density with respect to the first variable. It will be this one. I don't know if I will have the time to do this next session, but you have the exercise 5 of the list 5, okay, that define what are gamma distribution, and here you have an example of what is a gamma distribution. That is an extension and generalization of the exponential. If I don't have the y here, I have something that looks like the exponential, but with a y. Okay, so it's something that we are going to deal with next session. And finally, if I compute the integral with respect to the second variable, so it's a computation I have previously done, but let's do it again. So if I do the computation with respect to y, I have what to compute? I have indicator integral of, so y is greater than x, lambda square exponential minus lambda y dy, okay, to compute, and I don't have to forget that x has to be positive. And I have already done this job. What is the primitive of this one? It's minus lambda exponential minus lambda y, and I obtain this way here, lambda exponential minus lambda x, indicator function of exponential. In particular, I prove that I recognize here a density that is known from the course. If I have this joint density for a pair, I am sure that the first component, density, is the one of an exponential of parameter lambda. Okay? Last question. I start from a joint density. I prove that the density of the second component is this one. The density of the first component is this one. The last question is, are they independent? So if I check my result here, they are independent if and only if the joint density is equal to the product of the density function of each component. So my question is to know if the joint density is equal to the product of this one and this one. Yes or no? No. They are not independent. It's not possible to have this indicator function because I have x and y that are mixed inside here, and here I have just an expression depending on y, and here an expression depending on x. If I do the product, I don't recover this one, so they are not independent. Okay? And I will train about this topic. Okay, we will do several exercises concerning this topic. Okay, and I will finish my session by this today, and I will finish the next one with the definition of expectation and variance in the case of continuous random variable, and just my little result concerning how to transform pairs of random variables. Okay? See you next session.